Alright, so here we are with our last section of Chapter 1. In Chapter 1, Section 4, we're going to combine functions to make a new function and find a new domain. So we're talking about composite functions here. Alright, so we're going to start out with this piece here, and we did do this in Algebra 2, so hopefully this is a revisit. The idea is that we are given that g of x equals x squared plus 1, and that f of x equals the square root of x plus 3. And so all we need to do is what each of these things says down here. So for instance, the first one wants us to add the two together. Second one wants us to subtract them. Then it's saying to subtract them, but now f minus g. Over here, because of the lack of symbolism here, this should be f multiplied by g. And then over here they want us to take g divided by f. So all we need to do is find the following and then their domains for each of these new functions. So it is best if you can simplify, but the idea here is that you could potentially just take each of them and do the exact thing to them without simplifying, and you would still have the function and you could still find its domain. So here we go with the first one. Again, what you're going to do is take g and add it to f. So our new function is just going to be x squared plus 1. And then to that, we're going to add the square root of x plus 3. Now, because the square root of x plus 3 is within parentheses, we can't necessarily combine any of these two things. There's nothing to distribute. And so really, oddly enough, this happens to be our answer. So again, how do you find out the domain for that? All you need to do is graph it. So if you type into your y equals this exact equation, how it's written, you can see an image of it and then talk about the domain and where the x's exist. Of course, you can always look at what's inside of kind of a no zone. So inside of this square root here, remember you can't have any negatives or else you end up with an imaginary number which cannot be graphed on what we're looking for with domain and range. So basically I already know that if I plug in a negative 3 I'll get 0. And then of course negative 4 would start to get me negative 4 would start to get me negative numbers inside of here, and so we don't want that. So as we look at the domain, we do know that negative 3 is going to kind of be that leftmost point that we can have, and of course we can in fact include that because square root of 0 is still 0, and that's fine. And then it does in fact go to infinity, because looking at all the rest of the pieces, there aren't any other like denominators or things that will make issues with what we have. The other way of doing it, as I mentioned, was graphing. And so if you take a look at our graph, the problem is that the 10 by 10 graph looks like this. And so you're like, okay, well, it looks like everything works. But of course we do know, because we're a little bit more thorough than that, that we do have this square root part, okay? And so what happens is if you actually extend maybe to 20 being your uppermost and then 10 there, you actually end up with an image that looks like, here we go, like this. So as you can see, it does in fact look as what we thought earlier, which was just the quadratic equation, but if you extend the graph, you do see that it actually ends up stopping over here at negative 3. So always pays to zoom out, especially if they're giving you something and asking, well, what's the domain? There's probably some sort of restriction there. So that is the first one. The next example is g minus f. So now we're going to take the green one, so x squared plus 1, and now we're going to subtract the square root of x plus 3. Not a whole lot changes here when it comes to what we're going to end up graphing. So we're going to take y equals and we'll graph that. The only thing that's going to happen is because this negative, it's probably going to end up either I assume shifting, but it could also flip, so we'll double check. But my guess is that the domain, since it's the same thing, no more kind of no zones are being introduced here, is going to be the same domain. So you would just type that into your calculator. Remember, you're going to y equals So we have, x squared plus 1 minus the square root of x plus 3. And my graph is still going all the way up to 20, which of course is good to look at. So yeah, it looks like it just stretches it down a little bit. So again, visually, if you're talking about your visual going up to 20, you have another check mark, but this time it goes a little bit lower than the axis. But as you can see, it again stops at -3 because of the square root that's happening here. And so this is our domain there. All right. Moving on, the next one we're going to subtract. So we're taking f minus g. So again, we'll type into our y equals in order to find the domain. But the y equals f, which is the red one, so square root of x plus 3. And then to that, we're going to subtract the x squared plus 1. Alright, and so as we look at this, again, the only thing that changes is now one of the equations is at the front versus at the back. And so again, the only thing that we're looking at is this one here. So I am again going to assume, but we always want to check, that the domain is still going to be -3 included and then to infinity. So we will graph that one. So we can delete some of it and then subtract x squared plus 1. And then, of course, my window is the same because I'm lazy, so it still goes up to 20. And so as we look at it, there's not exactly something that goes up. It's actually now flipped. So we do have this image now, and again, that's at -3 where it stops. And so again, in that case, we still have, for our domain, again, ranges up and down, but for a domain, the farthest left it goes is -3, and then for how far right it goes is forever. So that's your infinity. Alright, so now we move on to multiplying them, which of course changes that, versus adding and subtracting, just kind of combines the same things, but a lot of times multiplying ends up changing a lot of it. So we've got, for our y equals, we're going to put f, which is the red one here, the square root of x plus 3, and we're going to multiply that by g. So again, we still have that same restriction. There is going to be something happening with -3, right? And then -4 clearly will be negative. But it is going to change the image here because of this multiplying. So again, if we go to our graph and plug into the y equals a multiplication, if you don't get the same graph as me, it's probably because you did not put this in parentheses, because it is this entire red function times this entire green function. So if you didn't put the parentheses, you wouldn't be multiplying by 1 to this red function. No distribution would happen, so you'd end up with a slightly different graph. All right, so taking a look at our image, we have a function that ends up stopping at -3, and then it does a little loop-de-loop and goes on up. So again, that 3 will happen, because remember, plugging in a 3 into this will get 0, and 0 is a number. But otherwise, our domain is actually, even though we've done a completely different operation, going to be the same. So that square root kind of takes over when it comes to identifying. So that square root ends up kind of taking over. All right. Then the last piece here, we're going to divide them. So again, just basics. You can just write the first one, which they have as g on the numerator. And then the second one, which they have as f in the denominator. If these were not in square roots, we would end up trying to simplify as much as possible, maybe factoring or whatever's happening here. But instead, we can just go ahead and write this in our y equals. Remember, the numerator here is going to need a set of parentheses around it. So the numerator is the x squared plus 1. And then that's going to be divided by the square root piece. X squared, just double checking. All right. All right. And so it looks like, -3. So it looks like it actually has an asymptote at -3. You can't, of course, necessarily tell a whole lot because an asymptote kind of makes it approach that. So I'm going to go ahead and expand my graph so I can see. So all I'm doing is changing the Y max under the window button. So I'm pressing window, going down to Y max, and I'm going to change it to like 40. Just to kind of see if you can see an asymptote forming, which you definitely can. So if you take a look at what it gives you, putting your Y max at 40, you end up with a pretty much straight line at -3 that then kind of curves and goes off in a slant asymptote, actually. So either way, there happens to be an asymptote here and then actually nothing over here. So when it comes to our domain, we're going to have -3 and this time not included. So just less than, because it is an asymptote, so it can't be equal to. And then we're going to have our x's, and then of course infinity. It continues on. So again, main idea of domain is just going ahead and graphing each of them, but if you don't have that option, you're always looking for square roots. Those are issues. Denominators, when are 0, are an issue. So just kind of checking around for things that become imaginary or undefined. All right, so the next piece, I think that's the end, yeah. The next piece is composite functions. So now instead of taking them and doing an operation to them, we're going to actually put one inside of the other. So this is something that we did in Algebra 2, but we just want to double check that we are able to put one inside of the other. So again, composite functions is what we're looking at. And they're denoted by, in this case, F-O-G. It looks like fog, but it's read as F of G, so this is kind of looked at as the O for of. And it follows the rule where F of G is this, which means G is inside of F. All right, and again, kind of have a definition down there. So, taking a look at what we have here, we're going to try an example of one of them. And so, as we look, we want to find f of 2. So this one is a little bit less intense than what we're kind of talking about here, where one function goes inside. In this case, we're saying one number goes inside. So we're going to take the number 2, and we're going to plug it into the f equation, which is up here. So basically we write it as f of, I'll start with f of x equals x squared. But the idea is that we're going to take that x, and what used to be our x, and replace it with 2. And of course, anytime you plug something in, you want to put parentheses around it, especially if it's negative. This one's not, but hey, good practice. And so our answer for f of 2 is 4. All right. Then they want you to take this f of 2, so basically they're saying 4, because that's what we just got, into g of x. So now we're going to take g of x, and we're going to plug that into x plus 1 in a square root. Again, what we're plugging in is the 2, so instead of the x, we're going to put, the 4, because that's what we just got in the previous one. And so we're actually trying to find the square root of 5, which is a decimal, so really not all that helpful, so we'll just keep it as the square root of 5. And so right now we've just found out that g of f of 2 is the square root of 5. Because again, the first thing we did was f of 2. After that, outside of that, we did g of 4, and which was the outside here. And so we end up with the square root of 5. So thinking of it here, all we need to do is plug 8 into g, as we did kind of in our first step, and then plug that result into f. So just letting you know, plug 8 into g, then that result into f. So if we do that, g of 8 is going to have the g function of square root, and instead of an 8, x will have an 8. So it looks like the square root of 9, or 3. And so then we're going to take that 3, that result, and plug it into f. And so f of 3, or f of g of 8, is going to be that value squared. And of course that value is 3. So 3 squared gets you back to 9. So find f of g of 8, it's 9. Moving on, we also have function decomposition. So thinking of the previous one as composition, this one is decomposition. So all we're going to do is take a look at what they give us and try to find what is the inside function, or inside of probably parentheses, and then what's the outside function. So this is up to interpretation, because technically any function could actually be x. And so if you want to just say that x is the inside function and then literally the entire thing is the outside function, that's fine. But of course we are trying to actually find two relatively complex or more complex functions. Alright, so taking a look at what's inside and outside, I definitely see that inside these parentheses is the square root of x, and so when I think of inside, I'm going to say that g of x is the square root of x. The outside then is going to be this cosine, and so I'm going to say that it's cosine, but instead of saying cosine of the square root of x, or even cosine of g of x, I'm going to replace that. So the piece that I already used up above, I'm going to replace that in my equation with just an x. Because eventually, yes, this will get replaced by this, okay? But right now, if it's looking at just the outside function, there is no square root of x inside yet, if you were going to make it composite. Alright, so moving on to a few more examples here. Whoops, drawing on there. We are going to figure out what each of these pieces are. So this one is not just two functions now. You can see that there's an h function, which is your internal function. There's an f function, and then there's a g function. So to help ourselves out, again, usually the most interior function is going to be inside of the parentheses. So we're going to just say that x minus 3 is the inside. So after that, then we're just left with what is our x now. That is squared plus 4. Okay, and so then the next piece that you look for, because again you're trying to make this as basic as possible, would be to kind of just look at the fact that one of them could be kind of added to the other. So the next piece that I'm going to use is x squared. And so the next function I'm going to say is x squared. And so if I take that x squared out, I now have x, which is added to 4, and so that must be your last equation. And again, if this doesn't necessarily make sense, sometimes it's easier to go forwards. And so if we look at how we're trying to do g of f of h, we've got g of f of h, which is x plus 4. But then we want our x to become x squared, as we have in the f equation. So we now have x squared plus 4. And then we want to make all of those x's into x minus 3. And so now we have x minus 3 that used to be x, which will be squared still, and then because of g plus 4. So again, this was just to check to make sure that it did go back to what we had originally. All right, the next piece here has a terrible example that I wrote by hand, but anyway, we're going to check the inverse functions. So what happens is the entire reason for composition is because to check an inverse, you're going to end up with just an x. So again, we do cover this in Algebra 2, but not necessarily as much as here. So the idea is that if functions are inverses, so meaning one of them, when graphed, would flip over the y equals x line if the other one is graphed as well. So if functions are inverses of each other, the following will happen. F of g of x, once made, will make x, and also g on the outside of f of x will make x. If it equals anything other than x, you do not have inverse functions. Okay, so even if it's x plus 3 or x squared, or even if they both have x plus 3, if they're not both x, then they're not inverses. So we're going to go ahead and show that these two are inverses, and so I am going to kind of take them onto the next page. But the idea is that f of x is supposed to be x plus 3, and g of x is supposed to be 4x minus 3, and rather than graphing them and see that they are inverses, we're going to algebraically prove that they are inverses. And this will be something that you'll have to do on the assignment a few times as well. So here we are with our f of x, and our f of x, because I can't remember, was x plus 3. And then our g of x was 4x minus 3. Double check. Yep. Okay. So first thing I'm going to do is find f of g of x. Doesn't really matter which order you do them in, as long as you end up with both options, one inside the other. And so, again, the way that I wrote it is noting that the red is on the outside, so I'm going to go ahead and write the red function first, so x plus 3 over 4. But then I'm going to erase the x and now write the g function. So again, parentheses are helpful, so 4x minus 3. Alright, and now I'm going to simplify, which wasn't really an option in the previous example, but now I get to simplify. So taking a look at our parentheses, the only reason you would need them is because you're going to distribute, but nothing here will be distributed. So if we take away the parentheses, we notice that minus 3 and plus 3 can cancel. So if minus 3 and plus 3 cancel, then we're left with 4x over 4. And then we note that 4 divided by 4 can cancel, and so we do have, in fact, x, which is what we want. Then we move to the next one, and that's where we're trying to do g on the outside of f of x on the inside. And so if the green one is on the outside, I take the time to write that one first. And then we erase the x and put the other function, which I did not leave a whole lot of room for, so I'm going to move my 4 over here. And then x plus 3 divided by 4. Alright, so taking a look at how we can simplify this, notice that this piece here is being both divided by 4 and multiplied by 4. So it turns out those 4's can cancel. And so we're left with x plus 3 minus 3, which of course we said earlier minus 3 and plus 3 cancel, and so this one also equals x. So now we know that f and g are inverses, because they did in fact both equal x. So that's the idea, and so when the assignment asks you to show graphically by graphing, but then also algebraically, this is what you would do for your algebra. They're also going to ask you to algebraically show if something is odd or even. And so we did talk about what it looked like in our previous notes, but now we want to actually go over the algebra of it. So this is the piece here that we're going to be looking for. If something is going to be an even function, if you plug in a negative x in for all of the x's, you're going to actually just get the original back out. Versus for an odd function, if you plug in a negative x, you actually get the entire equation back, but with a negative. So completely negative versus the same equation again. So, in that case, we're going to try an example, or a few examples here. Whoop. Alright, so here we are with telling whether the function is odd or even or neither. So, looking at this, remember that the idea is that it's going to be even if you plug in a negative x and get the original equation back out. And it's going to be odd if you plug in a negative x to the equation and get a negative version of the original equation. Alright, so our first option here is to take the equation, which we have, of f of x squared plus 3, and instead of an x, we're going to plug in, with parentheses, a negative x. So if we plug in a negative x and we go through identifying what's happening here, we technically have a negative 1 that is being squared and also an x that's being squared. And hopefully we know that negative 1 squared is actually just 1. And so officially we can actually get x squared, with I suppose a 1 if you wanted to keep that out front, plus 3. And so looking back at what we had originally, it was supposed to be x squared plus 3. We plugged in a negative x and still got the same back out. And so that must mean that this one is even. Alright, looking at the next option, we're going to plug in to the equation of x squared minus 3x plus 6. And into that, each of those x's is actually going to be a negative x, again with parentheses. And so we have negative x squared, the quantity, so we do know that that becomes x squared again. Negative 3 times negative x becomes a positive 3, and then plus 6. So remember that the original function was x squared minus 3x plus 6. And so since those don't match, it's not even. And then the odd option would have been negative of the entire thing. So negative x squared minus, oops, I forgot my x, minus 3x minus 6. And so plus 3x, wow, I'm having issues there. So minus plus minus, yeah. So again, you just look at each of these pieces and make them the opposite. And so if we take a look at comparing this with this, we notice, hopefully, that this one has a plus and this one has a minus. So remember that there are 3 options. It's either odd or even or neither. And so in this case, we are at neither. Alright, then our next one is supposed to be x cubed. So x cubed minus 2x plus 1. And again, we're replacing each of those x's with negative x. And so if we do that, hopefully we know that negative 1 cubed and x cubed will result in a negative 1 still and an x cubed. The next piece has negative 2 times negative x, so that's going to be plus 2x. And then the last piece doesn't change. And so as we saw in the previous one, even if there's 2 things happening for the other x's, if this one doesn't change, this one's actually going to be neither as well. It is neither the original equation nor the opposite of the original equation. And then the last one, going through that piece, if we take our negative x and cube it, remember that's going to end up with negative x cubed as we had in the previous problem. And then we're going to have negative 2 times negative x, which makes plus x. So negative x cubed plus 2x becomes our composite function, and if we look at the original, everything is opposite. So this one is going to be odd. Alright, so there's our assignment, and it's going to be the same as these types of examples, so good practice.